You may have seen this illustration before where a teacher surprises her students with a test, and it's a multiple choice test. The students haven't revised and so they guess each answer. There are 20 questions and each question has 5 options. So if we think about each individual question, the probability of a student getting the correct answer is 0.2. But if we define a discrete random variable to be the number of correct responses, there are 21 different possible values for x, ranging from 0 to 20. So do you think that these are equally likely? Is it just as likely for a student to get 0, 1, 2, 3, or 20 correct answers? Well, if you've done this activity before, you'll know that the expected value of x, or the mean of x, is about 4. So do you have a better suggestion? We can assume that 4 will have the highest probability and 20 out of 20 would have a low probability. So what would be your suggestion for the different probabilities for the different x values? This kind of distribution where each outcome has 2 options, in this case right or wrong, is known as a binomial probability distribution, and we're going to explore this type of distribution during this lesson. A tree diagram for a binomial probability distribution would look something like this. So this is a heads and tails flipping a coin tree diagram, but it could just as easily be passing and failing a test, anything with 2 outcomes. So we've got the probability of throwing a head each time, given as p, and the probability of throwing a tail would be 1 minus p. Now in the case of a normal coin, this would be 0.5 and 0.5. In the case of the previous question, where it was 0.2 for a pass, it would be 0.8 for a fail. So if we define x to be the number of heads when we flip a coin 4 times, then x can be 0, 1, 2, 3 or 4. The probability of throwing 0 heads means we're throwing tail, 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 and we're going to multiply along the branches. So back to the tree diagram, tail, 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 tail would be 0.5 times 0.5 times 0.5 times 0.5. To throw 1 head, it could be head, tail, 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 head, 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 tail, tail, head, tail, or tail, 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 head. Now each of those possibilities is 0.5 to the power of 4, and there are 4 of them. To throw 2 heads and 2 tails, there are 6 different permutations, and for 3 heads there are 4 permutations, and for 4 heads just the 1. Now imagine that we're dealing with a biased coin, or a situation like in the surprise test where p and 1 minus p take different values. So it could be 0.6 and 0.4 or 0.2 and 0.8. Now the probability of throwing 0 heads in terms of p is 1 minus p to the power of 4. And the probability of throwing 1 head is p times 1 minus p cubed, but there are still 4 ways of doing this. So it could be p, 1 minus p, 1 minus p, 1 minus p, or 1 minus p, p, 1 minus p, 1 minus p. But the combination still consists of p and 1 minus p cubed, and there are 4 of those. For 2 heads, there are 6 ways of doing this, and each way consists of 2 p's and 2 1 minus p's. For 3 heads, it's 4 p cubed, 1 minus p, and for 4 heads it's p to the power of 4. You may have noticed that these coefficients 1, 4, 6, 4, 1 are directly linked to the number of coins and the number of heads we're trying to achieve each time. If we have 4 coins and we want to choose 0 heads, then there's only one way that we can do that. If we have 4 coins and we're choosing 1 head, then there are 4 ways that we can do that. 4 coins and choosing 2 heads, 6 ways, 4 choose 3 is 4, and 4 choose 4 is 1. So if instead we were throwing the coin 8 times and we want to know what's the probability that 2 of the coins will have heads on them, we don't have to do a tree diagram, we don't have to do this table. We can instead go 8, choose 2, and then p squared, because p is the probability of throwing a head, and 1 minus p for the other 6 branches. And still with 8 throws, what's the probability that we have 3 heads? Well, 8 coins, choosing 3 heads, p cubed, and 1 minus p to the power of 5. And choosing 4 heads from the 8 coins, 8, choose 4, p to the power of 4, 1 minus p to the power of 4. And you should notice some patterns here. The number at the top of the choose symbol is the sum of the 2 powers. The number at the bottom of the choose symbol is the same as the power that p is raised to. So in general, if we're repeating a trial or event n times, and each trial has only 2 outcomes, A and not A, we say that the probability of A occurring is P, and because A and not A are complementary, the probability of not A occurring is 1 minus P. In the example where we threw a coin 8 times, N was 8, and P with a normal coin is 0.5, and so is 1 minus P. But if we have a biased coin that favours heads with a probability of 0.6, 1 minus P might be 0.4. Then we're looking at the probability of event A occurring X times. So that might be that in our 8 flips of the coin we get 3 heads or 4 heads or 2 heads. So X is our variable here. And for that it's N choose X, P to the power of X, 1 minus P to the power of N minus X. So remember, N was the number of flips of the coin in our example, so that was 8, choose, and then let's say 3 for X, then that would be P cubed and 1 minus P times 8 minus 3, which would be 5. An alternative notation for NCX is to write NX in those long brackets. We'll work through some examples so you can see this formula in action. So firstly, we're rolling a normal die 10 times, and we want to know what's the probability of rolling 3 sixes and what's the probability of rolling 5 sixes. Maybe you could have an estimate in your mind as to which you think is more likely and roughly what those probabilities might be. So our N is 10 because we're rolling the die 10 times. And we're counting the number of sixes, so our P, the probability of rolling a 6, is 1/6. In part A, we want to know what's the probability that we'll roll 3 sixes in our 10 rolls of the die. So that's 10, choose 3, and then 1/6 to the power of 3, and 5/6, which is the probability of rolling all the other numbers, to the power of 7. And in part B, Very similar, but replacing the 3s with 5s. So we're still rolling the die 10 times. This time we want to know how likely it is that we'll get 5 6s. So this time 1/6 to the power of 5 and 5/6 also to the power of 5. So try putting these values into your calculator. The probability of rolling 3 6s is 0.155 and the probability of rolling 5 6s 0.013. So that's obviously less likely than rolling 3 6s. Try this second example yourself before watching my solution. We're given the probability that a soccer player scores from a penalty kick, and that's 0.6. So that's our p-value. And we're told that he takes 8 penalties, so that's our n value. In part A, we want to know the probability that he will score 5 goals. So that's 8, choose 5. Probability he will score is 0.6. So we raise that to the power of 5. Probability he won't score is 0.4, and we raise that to the power of 3. 8 minus 5. And the probability he'll score at least 5 goals means it could be 5 goals, or 6 goals, or 7 goals, or 8 goals. So we need to add up all of these probabilities together to find the probability he'll score at least 5 goals. And you should check on your calculator that you do agree with these values.